Okay, welcome to the class. So, we have been doing alkali metals sensing. Okay. Now, we come to an important one, transition metal sensing. Also, you should have a feeling, I want you to have a feeling about these metal ions. What do they do in biology? Okay. Sodium ion and potassium ions are very important, and so are some of the transition metal ions like copper, zinc. I am not telling you the oxidation state, okay, but it is copper too. Copper, zinc, iron, okay, copper, zinc, iron. So, these are some of the metal ions, they are essential, okay, essential transition metal ion, essential metal ions. There are quite a few essential metal ion, transition metal ions are there, and there are, in addition to those transition metal ions, there are alkali metals, that is sodium, potassium, and alkaline earth metal, calcium and magnesium. Okay. These are called essential metal ions. I will show you today one curve. It is done in bioinorganic chemistry, but that is fine. I am showing you a curve for a particular metal ion. Okay. This is 0, this is minus, and this is plus. Minus means bad, plus means good, okay, good in the physiological sense for an essential metal, okay. And this curve goes like this. Let me change the color of the pen. So, suppose I am talking about the what is the curve look like for copper. So, when copper is almost very small amount, there will be minus here, very small amount or absent. Then what is the problem? We will have disease and we can die, because they are essential metals, they do all essential things, and then after certain concentration curve goes like that. But if you have excess copper, then we will have Wilkinson's disease, Parkinsonian, so many problems are there. So, we cannot have very small amount of copper, then it will be copper deficiency. We cannot have large excess of copper in our body, then we can have disease. So, there is an optimum range, okay, optimum range. So, this range is optimum, this is concentration. You must have heard about this one. This curve is called Bertrand curve. Okay. So, Bertrand curve of copper is like this, okay, I just made it up. For zinc may be like this, I do not know, okay, we have to see literature and find out. So, for different, I just want to emphasize that essential metal ions within a concentration window, they function properly in biology, okay. They will function properly in biology within a certain concentration window. So, this metal will, this is the concentration window, for this metal this is the concentration window, like that, okay. So, we have to, through fluorescence, we can detect if there is excess or if there is excess or less, all right, because fluorescence can give us an idea about concentration also, not very accurate, but an idea, okay, an idea about, because the intensity of the fluorescence intensity should give an idea about the concentration. So, that is why this is very important. Now, I will tell you the problems with transition metals. Transition metals especially paramagnetic ones quench fluorescence very effectively. Quench means if something gives fluorescence, then if transition metal is there, it will quench that. I am coming to that. Quench fluorescence. Okay, that is problem. Okay. So, now just a hypothetical, suppose I make a macrocycle, okay, which is very specific for say copper 2 plus. Copper 2 plus is a D9 system. Copper 2 plus is a D9 system. So, it is a paramagnetic. It will be paramagnetic. Okay. So, now if I put a, suppose I put a fluorophore here, any fluorophore. So, I write, when I mean any fluorophore, I write F. Okay. Suppose there is a nitrogen here, fine, here also could be nitrogen and all that. So, when there is, okay, let me remove this first. Now, this lone pair is available because this is empty, receptor is empty. So, if I excite the fluorophore now, what will happen? There will be PET. So, PET is on. PET is on means fluorophore is gone. But if I put copper, suppose I put copper, it likes copper, then what will happen? It will be engaged, this lone pair will be engaged to copper. So, PET will be gone, PET will not be possible. Therefore, what I expect? I expect is a strong fluorescence, but not really. I do not see any fluorescence, because this copper being a D9 paramagnetic, it will interact with the fluorophore and it will quench fluorescence. It will quench fluorescence very effectively. So, quenching fluorescence is also a way to detect, but that is not a good one. Okay. We want put a transition metal and then we see strong fluorescence, then that is very important. And you will be glad to know that in the world, we are the first from Kanpur IIT, we are the first who made systems where transition metal induced fluorescence enhancement is possible. Since then many people have done. Okay. So, now I will show you how this first the quenching. So, there are several mechanisms are in place for the quenching, to account for the quenching. These are number 1, conversion. What I am writing? I am writing the mechanism of quenching of fluorescence. Okay. I am writing mechanism for quenching of fluorescence by paramagnetic metal ions or transition non-paramagnetic metal ions as well. Okay. Conversion of electronic energy theoretically these are determined. People have done lot of work on that. To kinetic. Via collisions. So, this can be controlled if you take a very dilute solution, which we generally take 10 to the power minus 7, 10 to the power minus 8 molar, then the collision probability will be less. So, this thing, this number 1 point can be managed. Conversion. What is happening to me? I make a problem with the what I am writing. Conversion. Okay. Conversion of. Then 2 high spin orbit coupling. Spin orbit coupling. Spin orbit coupling in atoms, they increase with atomic numbers. Actually, spin orbit coupling are very high with heavy metals, and this spin orbit couple also can interact with the fluorescence. They also quench fluorescence. So, that means heavy atoms will strongly easily quench fluorescence. So, if I take copper, then silver, then gold will quench fluorescence through spin orbit coupling also, apart from paramagnetism. Then number 3, redox perturbation. Transition metals are redox active, so redox perturbation can also quench fluorescence. Redox perturbation. Redox perturbation, and then number 4, perturbation by paramagnetic, means an unpaired electron. So, by paramagnetic metal ions. And number 5, formation of charge transfer complexes. These things can be easily taken care of, charge transfer complexes. And then number 6, electronic energy transfer. Transfer of electronic energy to the metal ion, to and from metal ions or ion. Okay. So, these are some of the mechanism of quenching for transition metals. But I told you that transition metals are very important, because if we have some problem, if you have less metal, less copper deficiency, we have copper deficiency, or you have iron deficiency. Iron deficiency, all of us know that is causes anemia, right. We can have causes zinc deficiency, that can also cause lots of problem. Okay. These are very important transition metals. Well, zinc is not a paramagnetic, but it can still can quench fluorescence through other means. Okay. There are all 6. Okay. So, therefore, if we look at all these things, all these 6 mechanisms, one thing is very important. One thing comes out is that metal receptor interaction two important part, and metal fluorophore communication. That means, if metal receptor interaction is very great, very strong, that means metal binds to receptor very strongly, then we say metal receptor interaction is very high, and metal fluorophore communication will be low. Okay. So, these two we can play with to take care of all these 6 mechanisms. Okay. So, we were the first in the world to do this. We made, so we understood the properties of cryptands. So, let me write a cryptand, or the one that we used. Let me write like this. This is one of the receptors that we made, synthesized, and then we reacted with anthryl bromide to get this compound. Fairly easy method. fairly easy method. We synthesized this compound under high dilution at low temperature and got good yield of this product as colorless crystalline form, and then upon reaction of this we got a very pure product. By the way, fluorescence, whenever you apply fluorescence, the compound must be absolutely pure, that is very important. So, this compound we made, synthesized, and what is the property of cryptan? Property of cryptan is such that once you put a metal ion here, I put a metal ion here, okay, inside the cryptan, it is isolated from surroundings. So, let me write metal ion inside the cavity. Inside the cavity is isolated. Isolated from surroundings. In a cryptand. That is a property of cryptand, and it is bound very strongly. So, all the nitrogen lone pairs are now attached to this. That is number one point. So, my metal receptor interaction is very high. Is very high. And metal fluorophore communication is very low. So, all those 6 mechanisms I talked about, they are taken care of. So, when I excite this fluorophore, this what happened, I am writing this. This is the result. Okay. If there is if this cavity is empty, then we get like a okay, baseline. But if this cavity is occupied by this metal ion, we see this. That means, you see, when I put a copper, we see a tremendous fluorescence, okay, about very close to say 500 times, which is tremendous. Okay. So, we see 500 times time increment of the fluorescence. So, that is a very important discovery from our lab, and since then many cryptands were taken and modified and added anthryl moiety, and we got fluorescence signaling systems for transition metal ions. Okay. Here we have used the property of cryptands. Its property is, it is when metal is inside the cavity, it is covered from all sides. So, it is isolated from surroundings. So, your anthracyl moiety is outside. So, anthracene cannot interact with metal. Therefore, most of those all of those almost those mechanisms are not operational. So, therefore, we see a very strong fluorescence upon excitation. Okay. So, therefore, when we want to make a sensor for a particular metal ion, we have to know what type of property the receptor must have. See, since then we have done instead of anthracene, we have done with pyrene, we have done with just now I said, I again forgetting that, coumarin, okay, coumarin, this pyrene, body P, we have done so many fluorophore, does not matter. Fluorophore just gives signals. Depending upon its structure, it gives signal at a particular wavelength. So, depending upon what wavelength we want, we can choose, okay, choose the fluorophore. So, fluorophore is just reporter here, it is the reporter. So, it reports to us, but this one is happening in the microscopic world. One compound that is accepting a metal ion and we see very strong fluorescence. And from this intensity and all that, we can make a graph with a and from the graph we can find out the concentration of an unknown solution containing copper. One problem is that this cryptand has poor chemoselectivity. This cryptand has poor chemoselectivity. So, therefore, we see fluorescence increment with nickel 2, all the transition metals, first row transition metal, first row heavy metals, then mercury, okay. So, all kinds of dangerous metals we can see fluorescence enhancement. So, that way this is poorly chemoselective, there is no selectivity. So, all metals can be detected, all right. So, that is one of the drawbacks. However, for any transition metal detection, this kind of system is unique and this was discovered from our laboratory. We are first time discovered in 1995. Way back in 1995 we discovered this and people have recognized us for that, and there are many groups all around the world, they try to do this metal receptor strong, metal fluorophore weak. Another technique I will just see cartoon. You take a metal receptor here and make a very rigid. How do you can make rigid? Maybe you can write all aromatic groups to make it rigid, aromatic, okay. Aromatic and some whatever I am making all up, okay. And then here we say fluorophore. Here you say fluorophore. What will happen? This fluorophore cannot interact with the metal here, with the metal ion here, because it is very rigid. So, they are well separated. So, they can also have metal receptor strong and metal fluorophore weak, very weak. So, therefore, metal fluorophore communication very low. So, that is why these kind of systems also give fluorescence enhancement with transition metals as well as heavy metals. So, this idea of metal receptor interaction high and metal fluorophore communication very low has been taken up by others, and they have used other fluorophores, other systems. So, that you can also design on your own fluorophore and receptor. They will be well separated and very rigid systems, then they can also give strong fluorescence enhancement. So, I stop here today, and next time I will do more of this. We take a look at directly take a look at these things again. Thank you very much.